Let me show you the schedule first. Here is the schedule. So today we will cover the subsea plant engineering. But before then, I should finish up my last remaining lecture on underwater system. Then Adib will cover the first part of subsea plant engineering. And then finally, I will cover the second part of subsea plant engineering. And because there is no discussion session today, that will be the only lecture scheduled for today. Any question to any schedule or any other things? No, then I can start my remaining part of that lecture. I guess we stopped around here. So that the power source for the vehicle was covered at the time. So there is a surface powered means the surface ship provide energy, usually the electricity, through the tether, the cable, to the vehicle. And second one is vehicle powered, it is a self-powered. We need to use a battery or fuel cell or other things. Because the size of this ROV AUV is small, so we cannot use big engines. And hybrid system is a cable and also self-power. I explained about docking system, something like a fuel gas station last time. Now we move on to communication linkage for the especially ROV. They use a cable as a hardwired communication. So either electrical or fiber optical cable can be used. So it's very similar to landside communication as usual to our normal days. But underwater, without cable, there is a problem of communication. So most used method is acoustic communication using sound, and underwater sound modem is used for communication. That is the main option for the communication inside. So you can imagine that submarines heavily depending on the acoustic communication. So once there is a problem with the submarine, something like a disaster near Indonesia last month, the communication is stopped. So we cannot communicate with them inside the people. And there is also optical communication, but it is not popular because the distance is very short because of the water. So that near the surface, we can use optical or radio frequency, mobile system can be used, very shallow water. So the main option is acoustic, inside the water, deep water. And there are several examples of ROV on USA, and WHOI is Woods Hole Oceanography Institute. So it's a research institute. And depth capacity is 6,000 meter. Weight is 3 tons something. You can see the picture. Okay, there is one video. So then let's see.
Nobody's been down the bottom of the Perth Canyon before. Nobody with an ROV. Going 3,000 metres where nobody has ever gone before. There's challenge in that and there's victory in that. But what's more important is that we do it in a coordinated, engineered and managed way that we know what the outcome's going to be before we get there. This is special. This is an evolution point in TMT as much as it is a wet test. So this is really the culmination of a lot of people's input into this ROV system. Not only those around the table, those that fly it, those that build it, those that fix them, but everybody that stands in TMT, 108 people that we have on site at the moment, accounts through to purchasing, everybody that we have offshore has contributed in some way to where we stand right now with this test. You do have that, that nervous energy, not fear, but just nervousness that keeps you sharp. We're expecting it to go well. We build ROVs, that's what we do. So there's nothing contained in the test or in what we're doing that's new or different. We're just doing it at a deeper depth. Okay. So technically, I'm not really that worried about what we're going to do out there. Okay. But safety-wise, that's causing me not to be able to sleep. So when you're moving an ROV around that's 5 tonne, when you're luffing out a Lars, that weighs over 10 tonne, when you're operating a winch, that's what they pay for. So I guess it's with these cornerstones of functionality, design, robustness and simplicity that have evolved into the Typhoon class ROV. So the tests include making sure that we understand how we're going to launch the vehicle, making sure that we understand the vehicle is ready for the dive. So the risks don't end with the technical development or the implementation of the design. The risks don't end until that vehicle is safely back on the deck of the boat and the job's been accomplished. To do that, you need skilled people, you need good processes and systems.
Challenges, I guess, are that we're using a lot of but certainly in Total Marine Technologies history, this will be the that we're putting together for our client, which is TLO, and those will go and operate in Brazil for Petrobras. And a lot is riding on this test because there are a lot of other users who are interested in this type of ROV, and subject to this test going well, we believe there will be potential to build many more of these in the short term.
Okay, that's enough for today. And during that, this video is, I guess, is made by a company called TMT. They are operator of this ROV and provide a service. One company mentioned by the speaker is Petrobras, and Petrobras is an oil company from Brazil. So national owned, government-owned oil company. Petrobras is big company because Brazil has many oil fields there around the country. So TMT as a company, or ROV service company, they provide service to Petrobras. Right, so that, and then this is another one from MBARI. MBARI is another research institute in United States, but it's the West Coast. Uzor is near the Boston in the East Coast of the United States. embarked near the San Francisco. Monterey is the south of near San Francisco. And weight is 2.5 tons and depth is similar. And this one is from Japan. And JAMSTEC is also a research institute in Japan for the ocean. So the depth is 7,000, weight is 6 tons. Launcher is 6 tons. The vehicle itself is 4 tons. Right? And you can see from the right-hand side, there is 2 bodies, right? 2 portions of bodies. So there is a surface ship, and then there is another launcher. They are saying launcher. This one is bigger. It's a 6 ton. So it has a more probably big battery inside somewhere, and near the vehicle. Right? So it's some kind of station, submerged station, or base, or base camp or something. And this one is from Korea. Also, Moe and Korea is also a research institute. This one is nearby our campus. So we can drive to this institute by 10 minutes by drive. So we may have a time to visit there. So steps is also 6 kilometer, weight is about 4 tons. Okay. Another one, Minero. This one is ROV also, but it is for the mining of manganese modules at the bottom of the sea. So you can see that there is a manganese module is collected by this ROV and then processed on the surface to bring as a precious mineral. And towfish is a special kind of something like a glider. They are scanning, testing the water. So this one is an image captured by this scanning operation. And the scanner is made of acoustic scanner rather than laser scanner. So they only use acoustic sound devices for scanning the seabed. There is another video here. Let's see this.
On board the RV Resolution in the Boston Harbor, we've come here to see for ourselves how the Bluefin AUV operates.
AUVs like the Bluefin 21, they're the tool you would use to conduct a wide area side scan survey in ultra deep water.
Will O'Halloran is a marine operations engineer for Bluefin Robotics, which designs and builds these autonomous underwater vehicles in Quincy, Massachusetts.
If this were a mission, a real mission, what would it be doing?
So the next thing that would happen is the radio instructions we received to that red antenna there. The vehicle would say, okay, I'm going to start this mission. The propeller would spin up and then it would die.
Here in the Boston Harbor, the water is only about 40 feet deep, which is easily manageable for the Bluefin because this autonomous vehicle is used to working in depth several miles below the surface.
The Bluefin 21 can dive about 2.5 miles, but Flight 370's wreckage in the Indian Ocean may be deeper than that. It takes about 2 hours for the Bluefin to reach the bottom, where it can operate for another 16 hours. It scans the ocean floor as if it's mowing a lawn, using side-scan sonar, which identifies objects that stand out from the seabed.
When it's working with the side scanners, it's not actually taking pictures, right?
No.
It's measuring sound.
Correct. What it's doing is it's converting sound to electricity and then turning that electrical value into a numerical value, then turned into an image.
When it returns to the surface, scientists download the sonar data to computers. The results may look something like this.
And what we're looking at here, for example, this is a shipwreck in Boston Harbor. So you can see how it's different than the area around it. You can see there's parts of the steam engine right there. And
if something catches their eye, the Navy will send down a high-resolution camera on the Bluefin 21. It can take black and white photos covering about 15 square miles a day. It's a slow process, moving at just 3 nautical miles per hour, only made worse by horrendous conditions, freezing temperatures, mountainous terrain, and complete darkness. But even diving blind, there is much hope the Bluefin 21 AUV will see something. Randy Kay, CNN, Quincy, Massachusetts.
Okay, any question? No, then we can move on to AUVs. So before we see the ROVs, now starting with the AUVs. The video also was about AUV. And this is, you see that the size and weight is much smaller than ROV. Right? Not tons, only kilograms. Right? And also endurance is important because they use a battery. So for the ROV, you don't mind about endurance because energy is provided by the surface ship. But here it contains all the battery. Battery is the main power. So it's smaller and then shorter. And this is from Norway. And Kongsberg is a big company. And they provide this one also in less than 1 ton. So it's larger than before, but still less than ton. And depth and also endurance is a maximum 24 hours. And speed is 2 meters per second. And this is from MIT of the United States. And so the size is smaller, weight is small. It is coming from university, so it is not so big. Company provide a big one, about 1 ton, because they have money and also purpose. This is for university and for the research. And Uzor, once again, this is a research institute, so that they have a little bit bigger size, and depth is 6,000. Endurance should be about 1 day. And this is from also Jamstec of Japan, a research institute, and weight is about 10 ton. It's a big, right? AUV. And also distance is 300 kilograms. They do not provide hours. And depth, 3,000. And it is from Korea. Also the research institute nearby, Kordi on Moeri. Now it's Kriso. And very small, right? 20 kilograms. And only distance, not time. But they're very short, right? Comparing to this one is 300 kilometers. In Japan is only 10 kilometers because of the battery size. And glider. Glider is interesting, so that they do not use power as much as possible. So they use only power for the buoyancy collecting, air compressor. So that once, because this is battery powered, but they can travel from long distance. I guess this is east coast of United States. And also this is west coast of Europe, somewhere in Spain or Portugal, I guess. So the gliders can travel this long distance, something like 1,000 kilometers, 3,000 kilometers, something, by using only buoyancy. So once this is same as glider in air, the glider does not have any power, but they fly some distance by using air and wing, right? Very similar to here. So they travel some distance by using moving down and very slow motion. This is exaggerated, but this way, once they are deep enough, then they use battery power to collect buoyancy up so that the system, the vehicle can move onto near the surface and then they stop the compressor, so that then they can dive down, and then also again energy is used for the up motion. So only for the up motion, you need only small pumping of air, right? Small energy, so that you can travel very long distance. That is the idea. And also communication is done once they are on the surface, near the surface. So they send data they captured something like image something. And this is a glider from Washington University. So small, but range, you can see that distance they can travel is 5,000 kilometers, even though the weight is only 50 kilograms. Lighter than myself. Length is also similar to me. And another one from United States Research Institute, also 60 kilogram, but the endurance is 30 days, or sometimes they use years of operation by using thermal battery, solar battery something, or thermal battery. And semi-AUV is a mixture of, this is from Korea, Korea. So it is AUV and ROV, a mixture. But they have a mission in University of Hawaii. All right, let's see. Questions? No question? Then we can go on to lecture by Adib, please.
Can you see my screen?
Yes, you can see and I can hear you. Yes, go ahead, please.
So today's class is about subsea plant engineering. In today's lecture, we will go through several notable subsea plant engineering, and we will try to get an overview of what subsea plant engineering is, what it entails. And then in the next lecture, Professor will go through the terms in much more detail. So, all right, so what is subsea plant engineering? Subsea plant engineering is the engineering where we extract natural resources such as oil and gas from the seabed under the sea. So this project here, it's called Pluto, and it's it's called Woodside Pluto project, and it was discovered in 2005 at Northwest Shelf area of Australia. So around here, this is Australia, and they discovered a reserve over here, and the water depth is around 4,000 to 1,000 meter, and
We may lost connection to Adib, telecommunication from Bangladesh. Okay. So this is about Australia, west side, a little bit north of west side here, the corner of west north corner of Australia. Okay, he's out and probably coming back. Okay. 벼락캐션을 안 들어왔군요. 아. 호주의 북부에 인도네시아가 있어요. 굉장히 가까워요. 그래서 거기에 뭐 인도네시아 사람들이 배 타고 어디 호스테클 오케이.
Sorry about that.
배. 네.
My internet is sharing screen. That's me. So as I was saying previously, this project Woodside Pluto project, this project has a potential to increase Australia's revenue by 5.5 billion Australian dollar, and it also has the potential to create more than 4,500 jobs. So we can see that subsea plant engineering can account for a large amount of a country's economy, and it also has the potential to create a lot of jobs. So this company called Woodside, they are contracted to build the Woodside Pluto project. And this is a large overview of the Woodside Pluto project. So what we can see here is that so subsea wells are created, and this is the ocean bed. And wells are created to extract natural gas from underneath the ocean bed. And by using a riser platform, we can see that the gases are transported, and this is called a trunk line. It's transported to an onshore LNG plant where the natural gas extracted from underneath the ocean bed will be processed. So this is slightly different from what we have learned before. Previously, we covered CPF, Central Processing Facility, and FPSO. And they usually do the processing of natural gas on the sea, but in this case, it's onshore. And we can see that there are LNG tanker. This is basically to export gases and stuff. So this is a very large overview of what a project looks like. This is another project. It's also near Australia. It's called the Impex ET field. So this is Australia, and this is the field. This is near to West Timor, East Timor, and Indonesia. So pretty close to both of these countries. So this ET plant is approximately 200 kilometers away from the Australian mainland, and its water depth is around 250 to 270 meters. So it's substantially more shallow than the previous plant. So the ITSI project is notable because they contracted South Korean company Samsung Heavy Industry and Daewoo to build the CPF, Central Processing Facility, and the FPSO, floating production storage and offshore vessel. So these are large projects, as we can see. The Central Processing Facility in itself is about $2.7 billion, which is contracted to Samsung. And the FPSO project is about $2 billion contracted to Daewoo. I believe the ships have been constructed and already delivered to the project. And so this is the rough site, like the one we saw before, Australia, and this is where they're basically planning. This is the HE field, and this is how they're planning to conduct the project. So what is a central processing facility? So this is what a central processing facility looks like. It's a semi-submersible hull structure, which means that it is submerged halfway through, and not exactly halfway through, but yeah, it's submerged. It's not fully submerged, basically. So it has 4 legs, semi-submersible hull structure, and it has 4 groups of 7 moving legs, and its design capacity is 1,657 atmospheres of export gas, and it has numerous flow lines connected by manifolds to the production train. And then it also has a dehydration plant in here. And this basically removes water or any kind of mud from the gases which are extracted. And so, for example, this is tritone glycol gas, and they dehydrate over here. And then it also condensates the natural gas, and then it exports it to the nearby FPSO. So the gases are extracted from the seabed, it's processed over here, and then it is sent to the FPSO. And then there is an offtake tanker, which, like, after processing it, it takes the gas from here, and then it takes it to the where it needs to be taken. And this also has an accommodation for 150 bed, so people working here can sleep and stay over here as well. So yeah, these are basically these are the details of CPF, and similarly FPSO also has several details. It has a turret mooring. We will discuss about this later on. And then it has capacity to store about 1.2 million barrels of oil or gas. And then it also has treatment and stabilization processes, mercury removal, and also water treatment facilities and stuff like that. So this is what a turret mooring is. So I think this picture does a better job. So in here, these red, blue, green lines are the riser pipes which transports the natural gas and oil to the FPSO. So the problem here is due to due to water tide and even wind direction, and the water is not stable. So this can make the ship rotate, heave, sway, and this has the potential to potentially break these riser lines. So what they did was all of these riser pipes are connected to this central pivoting object, and so the ship can rotate, but this thing here stays stationary. So this ensures that the riser pipes are protected and it does not break. So this is what a turret mooring is, and it's a very important and very expensive part of an FPSO. So this is an overview of what is included in a project like that, and we can see there are a lot of stuff over here, and each makes one part of the project. And we can see that CPF and FPSO is only one part of a very large project. So there are a lot of other things to do as well. So yeah, these projects are very big, this is called a field architecture. So in here we can see the company contracted to build the project, and this is the site for the CPF and FPSO. The black lines we see here are the third mooring angles, the third mooring, and the red and green line, these are the pipelines created underneath the sea to transport the natural gases from this well. So this circular object we see here are well. So well are like the places where natural gases are extracted after being drilled. So we take the crude oil or natural gases from the well, we transport it to the CPF, and then we transport it to wherever it needs to be taken to. This is another project called the Apache Vincent Black oil field. Similarly, we can see an FPS over here, riser cables connected to wells. So there are 10 wells here with 2 manifolds, and it uses one gas injection and 2 water injection well. So, and the risers are flexible. So, so yeah, but gas injection and water injection well, when gases are extracted or oil are extracted, we need to fill it with something. So we usually fill it with gas or water. And so these are the building blocks of field development. So at first we need to consider the reservoir. So we need to explore the seabed and find where natural reserves are. And we usually do that by drilling or by exploring the waterbed by numerous ways. And then the next part is the hydrocarbon production processing. So in here, we determine if the reserve is a gas or oil field. And we also need to determine the composition of gas or oil, this and the percentage of gas oil present over here. This is important for processing, as our development plan will depend on the composition of the hydrocarbon in the reserve. And then we need to do subsea production options, and then we also need to take care of health, safety, and environment. This is important because we have seen numerous tragedies. So I think in one previous class, we saw a video about a CPF getting caught on fire, and a lot of people dying on the CPF. And also we have seen cases, for example, the BP oil spill. So health, safety, and environment is a very important part, as a disaster can happen. And then there are economic section of the plan as well. So final investment decisions need to be taken, field development plan needs to be created, etc. So in here, a comparison chart of several fields are given. So among these fields, we have talked about the Pluto field and the ET field. Similarly, there are other fields as well. And what this is basically a composition of the chemicals stored underneath the in the reserve. So for example, in the Pluto plant, these are the percentage of chemical. We are mainly interested in LNG and LPG. LNG and LPG. We can see that most of these plants are high in natural gas, reserve, and that's mainly because we are trying to extract natural gas. So we chose reserve which are high in natural gases. And comparing the Pluto field to each field, there is 83% LNG in Pluto and 70%, but like for the LPG part, Pluto has less of it compared to each. So this gives us a good understanding of how much gas we can extract and how much it can add to our economic value. So as I told before, this is what the typical composition of field looks like. So it has gas, oil, and water. Then there's a well over here. We drilled through the reserve, and then we drilled to the point from where we want to extract what we want to extract. And then there are manifolds. There are manifolds and riser cables to extract the gas, process it, and then separate it. And then it goes from here to a CPF or an FPSO for processing. This is a video which is share the screen. So yeah, this is a video about an overview of subsea engineering. I will mute the audio. So this is what a CPF would look like. And then it's transported to the reserve. And then it's taken on. So you can see that in here, there is an ROV. This is controlled by an operator. So, sorry, I believe this is a management. And then the appropriate equipments are taken underneath the water. And then it is connected to the appropriate equipment. An ROV is used to do the operation because this is the water depth is very high, around 1,000 meters or so, and humans cannot operate over here. So an ROV is used to do the operations. So it's connected. Similarly, the ROV guides this connection as well. And then the ROV the appropriate wires. So yeah, this is basically how plants underwater plants are created, and they're mostly done by ROVs and robotic structures like that. So I hope this gave you a good overview of what subsea engineering looks like. Thank you for listening.
All right. Good lecture. Thank you. Any question to him? No. Okay, then we can have a short break and then return back to have my final lecture. Right. So we can return back. This is 47, so we can start at around 50. 3 minutes break, please. Subsea plant engineering. And I will cover the production, Christmas tree, pipelines, and riser, and burst, and corrosion problems. So what, return back to the original question that why we need subsea engineering. You can see that it is meaning of subsea is a deep sea operation, deep sea engineering operation, rather than sea surface engineering. From this picture, you see that there are FPSO or something like a ship-like object are floating above the ocean surface. And with that ships, we can say that there is a sea surface engineering. But comparing to that one, subsea or deep sea engineering means operation near the sea bottom. Why we do this engineering here? Because of the depth of the water. When the water depth is shallow, or even in the land side oil field, you don't need to worry about subsea engineering. You're just pumping out the oil and gas and then processing at the site, at the land site. But if the water depth is going deeper, something like 1,000, 2,000, 3,000 meters, then the riser cost is going higher. And also the speed of pumping from the seabed to the surface ship, it takes time and cost. So the engineers want to process the crude oil or gas coming from the well at the site near the bottom of the sea. And they just want to, in the long future, it may be possible that they process all the crude oils there at the deep near the bottom. And then they just extract the precious, economically valuable oil and gas and other chemicals only. And then remaining can be discarded or maybe refilled into the reservoir, return back to the reservoir. That can be the trend in the future. That's why, because of the water depth is going deeper and deeper, there is more need for having more and more deep sea engineering. So there are trends that more and more devices are developing to process chemicals near the bottom of the sea, right? So that then the ships can only transport the valuable resources, minerals, chemicals to the market. There is no need for the subsea engineering. Now, okay, there is a video already starting. Right, so let's see the video once again. Subsea gas compression plant in the world.
"200 kilometers off the coast of mid-Norway, Statoil has made a quantum leap for value creation and resource utilization on the Norwegian continental shelf. The project started as a mere dream 3 decades ago. But after years of innovation and development with our suppliers and partners, Statoil has now fulfilled this dream. 300 meters below the surface, the world's first subsea gas compressor facility has reached its destination. The pioneering installation, covering an area the size of a football field, could fetch an additional 282 million barrels of oil equivalents from the reservoirs under the seabed. In energy terms, this equals 4 times the yearly hydroelectric power production in Norway, or enough energy to power all households in the United Kingdom for almost a year. Compared to a compressor on a platform, Åsgard subsea compression substantially reduces CO2 emissions and is far more energy efficient. Let's have a look at how it works. As gas is taken out of the reservoir 2,500 meters below the seabed, the pressure decreases and the flow crawls to a halt. The compressor is then installed to actively suck out more gas and condensate from the geological formations. First, the compressor cools the incoming components and separates fluids from gases. The gases are then compressed, cooled once more, and mixed back with the fluids before being pushed to the receiving facility at Åsgard B. To avoid fluid blockage in the pipeline, the compressor maintains required flow at all times. The key to the subsea compressor's efficiency is its proximity to the wells, allowing both sucking from the reservoir and pushing through the pipeline. The subsea gas compressor on Åsgard is also vital to the next step for subsea processing, the complete subsea factory. Constructing self-contained seabed installations will increase safety and efficiency and grant us access to fields that have been unreachable in the past, an important step for our future value creation.
Okay, Statoil is oil company of Norway, national. And also they are talking about subsea factory. So they are moving more and more facilities down to the deep sea seabed. Right, so that's covering the idea. Big facility, large factory-like facilities going down toward the bottom of the sea. Right, so layout, typically there's a umbilical is for cabling to ROV, but manifold and pipeline, flow lines, and trees, Christmas trees and wellhead. There is a hole, well, and for each wellhead there is a trees. Trees is for the, say, overflow or stopping, emergency stopping device, something like that. We see it in here. And then manifold and collecting these pipelines, and through this more bigger pipeline, finally arrive at the riser. Riser is moving the flows, oil and gas, toward the surface of the water. And then there is a host facility, topside, centroid controls. So FPSO or something, or CPF is located there. So that is a usual field layout in deep sea, subsea operation. And as you see from the video, that the facility size is getting bigger and bigger. You see that there is a person here. So you estimate that the size is about 100 meters wide, something. Okay. Here is a 2-person again. Okay. And also big trucks are there. So these facilities, there is one and there is another one. So they are going down into the deep sea. And Christmas tree. And there is an onshore. Onshore is a land side. There is a oil and gas reservoir also, but now it is getting emptied, because for long history we already pumping out all the oil and gas from the land side reservoir. So now we are going back toward the deeper ocean to collect more oil and gas. But it is difficult and need more cost to pumping out. Right? So offshore trees, the same, the role function is same, but size is bigger comparing to the human body. And so that function is same. It is located at the wellhead, just above the well hole, and it is trying to blocking the oil or gases coming up. Once the reservoir is drilled, the gas pressure is high, so they going up as an explosion, very similar to explosion. So this device is trying to stop and also control the flow. So this is a subsea wellhead. There are the TGB, PGB, and there is a short name of that was explained by Adib in previous lecture. Housing, abandonment, and assembly, something like that. And 3, so wellhead is here. There are valves, several valves. They trying to stop and also open and close the flow lines, right? So this is a very complicated device, but it's still a kind of complex valve, opening and closing down the pipeline. And it is from Wikipedia. Christmas tree is an assembly of valves and spools and fittings used for oil and well gas, water injection, and other types of wells. And trying to control pressure provided Christmas tree on top of the wellhead, because the pressure inside the oil reservoir, gas reservoir is very high at the beginning, especially. And here is the components again, and this is standard of ISO. They have standard components, layouts, and assembly of this kind. And here is one video, so you see this one again for the Christmas tree, subsea vertical tree system.
Landing string technologies to assist in conventional subsea Christmas tree completions. Before completing a well with a conventional subsea Christmas tree, a drilling rig is placed over well center and drilling operations are conducted. The subsea blowout preventer, or BOP, is deployed from the rig with a marine riser. This provides a conduit between the BOP on the seabed and the rig at surface. The marine riser also provides the conduit for any intervention into the well during drilling and completion operations. The BOP is lowered until it is just above the wellhead. All of the subsea infrastructure will be inspected by a remotely operated vehicle, or ROV, which is controlled from the rig and gives real-time images from its cameras to the operators on board the rig. The BOP is then landed on the wellhead, utilizing the support from the ROV operator, and is locked into place hydraulically via a control umbilical from the rig. The connection between the BOP and the wellhead is then pressure tested to confirm integrity. After the BOP has been deployed, all drilling operations will be carried out before the completion is installed. With drilling operations completed, the completion is then installed using the X-Pro Landing String Assembly, or ELSA. This monobore X-Pro system comes complete with a specially designed lower adapter to provide annulus access to the dual-bore tubing hanger. This ELSA system also incorporates an orientation helix, which aligns the dual-bore tubing hanger to the correct orientation with the use of a BOP alignment pin. Once the alignment sequence is complete, the tubing hanger is then landed and locked into the wellhead with the application of hydraulic pressure. This hydraulic pressure is configured within the BOP stack so that the BOP independently controlled fail-safe ball valves and an emergency disconnect system. Also within the X-Pro landing string, you will find a retainer valve and lubricator valves. hydrocarbons from the well will flow up through the Expro landing string and back to the well test package on the drilling rig. The subsea test tree can be closed to isolate the well at seabed level, providing a gas-tight seal and containing the hydrocarbons below the closed valves. With the subsea test tree closed and the well isolated, the emergency disconnect latch can be disengaged to allow the landing string above the subsea test tree to be retrieved. The retainer valve is closed to retain the hydrocarbon column above the valve, and also vent any trapped pressure between the subsea test tree and retainer valve. The subsea test tree would then unlatch and be lifted clear of the subsea test tree valve section. This can be to allow the passing of bad weather or to disconnect from the well in an emergency situation. After the emergency conditions have been controlled, the subsea test tree latch section can be reconnected to the valve section and the retainer valve reopened. The interface between the latch and valve sections of the subsea test tree can be pressure tested against the upper subsea test tree ball valve to prove sealing integrity before the ball valves on the subsea test tree are both reopened.
Okay, so they are saying that when there is a bad weather, there is a storm is coming, then sometimes they need to disconnect the connection from the wellhead and piping line. So in the case, also for the closing time, somehow the reservoir is closed, then they want to disconnect the pipelines. That kind of thing is controlled by Christmas tree. All right, so then we can go on to subsea manifold. Manifold is just combining or distributing pipelines, gathering or distributing. So usually they're gathering from the well. There are several wells around the manifold, so the pipeline is coming toward the manifold, and then it is going toward the bigger flow line to the riser. And pipeline is coming back and together collected, and then manifold is here, and then also riser is here. Okay? So flow line is used to the wellhead to riser foot. And pipeline design process. There are many steps for each engineering process. So I will not explain all the details, but diameter is fixed by the capacity of pipeline. And installation. So the pipeline should be installed. So this one is a roll of pipelines. Even though this pipe is made of steel plate, but with a big diameter, it can be rolled into similar to the cables of electricity. The copper cables is also made of metal, but it can be rolled in like this one. So with a big diameter. So also the pipeline is bending like this one by their weight, self-weight. So this is a ship for cable landing, pipeline laying out operation. Okay. So this is touchdown and something like this. So this is a real operation, looks like this. And once again, the layout of well and control system, manifold, and Christmas trees, manifold tie-in system, and then subsea. Sometimes it is processing, something like separation and liquefaction, as you see the video before, and it is going up and riser and to the storage. Or sometimes there is a site for the drilling, for the new site is development. New reservoir is explored. Okay? So this is a typical layout. And this is drill bit. See, very big comparing to the human body. This one is used for making holes, drill holes to arrive at reservoir. It's a big size. And see also the riser, and then there is a drill pipe and riser. There is flow. This is Christmas tree or blowout preventer. Right. But there is layers of pipes, and the drill bit is here. Drill bit is at the top, and then they gathering water and mud and other blocks and then pebbles. They can be going up and down and again, and filled with another water and mud. RO is here. It says Christmas tree and other operations like this. And riser. This is for production. So once all the setting is done, you need to pumping out the oil and gas. But inside the riser, there is many layers of covers to protect. But also inside there is two big pipelines. It is gas lift and chemical injection and control the cables, electrical control lines, and other things. And size, you see that there is a 10-inch or something like that. That is a usual size. And low pressure, high pressure drilling and risers. And this picture is I took from United States. ABS is American Bureau of Shipping, the Classification Society. There is a real display of cutting of a riser. So you have a small pipeline inside big riser. And flexible risers, see if the water depth is something like 1,000 meters, then you can imagine that the weight of this pipeline is very high. Okay? And then the connection to this FPSO or CPF or floating body, the whole weight of this pipeline is hanging at this point. So it is very dangerous to the buoyancy. Also, the pipeline itself should be, the connection, the strength of the pipe, it should be very high. So they need to find out ways to lower down the total weight. That is the idea, so that they provide some kind of buoyancy in the middle of this, depending on the depth of the water. You can use more steps to lower down the weight, collecting of weight. So anyway, that is the way that they use flexible risers. Okay. So there are several different types, but basically they provide buoyancy, something like when you swimming in your swimming pool, you use some buoyancy plastic on your body or arm. That is very similar. So flotation attached to the riser. So buoyancy is supplied by these modules. So you need a clamp to attach this buoyancy module to the pipeline. And this is a buoyancy module with a clamp. Okay. So, and also they may protect the overbending of the riser. Sometimes there is a big force is coming. And hybrid riser is a combination of flexible jumper and relative. So they accommodate relative motions too of floating body. This is ship like a floating body. Because of the storm and wind, they can move and rotate. So the riser can be disconnected from the motion of the floating body. And then burst. Sometimes the pipeline can break. Then it's very big digester because oil is coming out, gas is coming out from the pipe. Then pollution is big, right? Dangerous and pollution. So this one should be minimized. And but because this is made of steel plate or mineral, so it can be break. And also failure is coming near the connection between pipelines, and also valve, and burst because of the high pressure, and also deterioration of the pipe riser, rust. So corrosion is also, because it takes 10 years of operation. So, and also salt water is not good for the corrosion. So you need to provide, because of the salt accumulation, so you need to have a chemical way of painting or electrochemical interactions sometimes. Oh, there's another video. I'll skip over because of time. You may have a to protect the pipeline by using epoxy coatings and for the eco-friendly technology. Right, that's it for today. Question? No? Then we'll see you on Thursday. All right, bye now.